Hello, everyone. Hi, my name is Madhav Alapati, and in this project, I worked on predicting Amazon review ratings from text user history and product history. This class is obviously for CSE 258 web 9ing, and for my project, I decided to use the Amazon 2023 product reviews. The high level idea here is that given an Amazon review, can we predict whether the star rating the user gave using things like review text, what the user usually rates, and what product usually gets rated? And on top of this, can we use additional products such as price or category? I also want to add that we're not just using the regular rating prediction here. We're also doing sentiment classification. So we're going to group things into positive if it's rated as 4 or 5, and then negative it's rated as 3, 2, or 1. And then this is additionally on top the regular 1 through 5 user product rating. So as I mentioned before, we're going to be using rating prediction. And for the features I want to use for that is going to be user history. And this is the average rating that the user has given in the past and how many reviews they've written. We calculate that over here. We are also going to be taking a look at the product history, the average rating that the product has received and how many ratings it has. And we also want to look at and have a sentiment analysis on what the actual review was, what the text was, so the current review. And beyond this, we're going to be looking at the metadata. So just things to see if it was a verified purchase, the price, and the main category, if these factors play an effect on what the eventual 1 through 5 rating was going to be. So in order to evaluate how we're going to be doing this and evaluate our accuracy, we're going to be using two metrics: root mean squared error, which is going to penalize more for larger mistakes, and mean absolute error, which is much simpler to interpret, and it's the difference between the stars and the true rating. For example, an MAE of zero point 0.6 means that I would be off by a little over half a star on average. I'm going to be taking a random subset of the millions of ratings we have, and I'm going to use an 80, 10, and 10. I'm going to use 80% of the data in order to train my models, and then I'm going to use 10 in order to do hyper tuning and validate it, and then test a final holdout test in order to see whether I'm overfitting or not, and to check my true performance. Here we can consider two baselines. The global mean baseline, which just predicts the average training for a review, which is very simpler. What it does is just takes the average rating that that product's been given and it assigns it that user product interaction. But we're also going to be doing as another baseline is using the user and item mean. So all the averages that the user has given out on reviews, but also the product's averages, and then take these two as a mean. And that's going to give a little bit better of a baseline, I suppose. But keep in mind, these are still baselines. For the second task, we're going to be using text, and in order to evaluate whether it's positive or negative, it's sentiment analysis, and we're going to evaluate with an F1 score, and we're going to use accuracy. So in overall, as an abstract, the project is going to be one main regression task and one additional sentiment classification. Now I'll briefly walk through the data set and how I load and pre-processed it. I used the Amazon reviews, as we've mentioned earlier, but it is extremely large. It has over 500 million ratings, and it spans from 1996 to 2023. Since it has so many categories, it's impossible to use everything. So for the purposes of our project, we decided to trim it down to just baby products. I'm working with the baby products JSON file and the metadatas, which is specifically for the big data products. And in order to avoid bias from just loading, the first subset in the first couple of years or the end couple of years, we use reservoir sampling to randomly sample 1 million of these reviews. What this does is this allows me to have an unbiased random sample as seen in the code, and I'm able to come back with 1 million of the regular reviews and about 217,000 of the metadata reviews. And when we look right here, I verify everything by checking the shapes, previewing the columns, making sure that everything is in fact as it should be. And we see that all of the particular, like the parent ASIN, the ASIN, are there. These are the necessary columns and rows. And we can also check the head to make sure everything is processed correctly and we've loaded the correct data. Now, what I'm doing here is I'm merging the ASIN with the parent ASIN. That means that these are grouped together by different product variants. So if there's a missing ASIN, I'm able to merge it with the parent ASIN. After merging these columns, what I have access to now is the category, the price, the average product rating. And then now we can take a look at the distribution of the data. We can see the distribution of ratings lean closer to 5 stars with very low ratings. And when we look at the rent, we see that they're very low, and but there's a long tail where people write detailed reviews. And in terms of price distribution, if we clip out the 99th percentile right here, we see that most baby products fall into a reasonable price range, and obviously the long right tail. Yep, we can see it right here. And in order for obtain like the training, the validation, the test, as I mentioned earlier, we're using an 80-10-10 split. And the key concern here, if you can see the code, is data leakage. So what I use is I only compute all the user and product statistics only on the training set. And the reason we don't want data leakage here is that we don't want data from the test set or the validation set in order to creep in. What this will do, this will artificially drop the MAE and the RMSE. So what I'm doing is I'm computing user mean rating and count, product mean rating and count only on the training set, and then I'm merging that back into the validation and test set. What I'm also doing, as you can see here, is I'm handling metadata features. If an Amazon provides an average product or rating, I'll use those. Otherwise, I fall back on the trading sets. And we see that we have the feature columns and we have the data split accordingly. At the very end of this process, every data point has a user and product history, text and title, purchase and helpfulness singles, as you can see here, and product pricing and category features. Finally, I define an evaluation function that reports RMSE and MAE. And this is the main metric that we're going to be use this helper function to calculate this model and compare them.
Hi, my name is Dominic Colucci, and in this section, I'm going to be walking through section three, where I explain how we formulated the problem as a machine learning task and then compare the 6 models that we implemented. So for this project, we formulated rating prediction as a supervised regression problem. Um, Inputs include user history, product history, um, and full review text are and full review text. Output is a real valued star rating between 1 and 5. The output being minimalized prediction error, and then the minimized mean squared error, and records to the RMSC metric, which corresponds to the RMSC metric we report later. All these models are trained on training split only with hyperparameter decisions made using the validation set. This task is well suited for the family of models we've learned in this class, including bias baselines, collaborative filtering, and linear models with TF IDF text features. So for the first model, the global mean model is the simplest baseline possible. It always predicts the average training rating, which my data set has a 4.2120 stars. This requires almost no code, and I compute the mean once and create prediction arrays filled with that value. The performance here in the test set was an RMSE of 1.32 and an MAE of about 1.05. This baseline is pretty weak and off by 1 star on average. That's what these numbers pretty much tell, especially that MAE. But it gives a lower bound for all other models. Next, we implement the user item mean baseline, which captures simple user bias and item bias. Using only trading data, I compute each user's mean rating, each product's mean rating. And in this code, this is just grouped by user ID and parent ASIN and mapping the means back. So for a new review, the prediction is simply the average of the user's mean and the product's mean. The performance here for the test was RMSE of a 1.28 and an MAE of 0.9853. This reduces error relative to the global mean, showing that even simple collaborative information provides a real signal and improvement in review and error in the review prediction. Third model included latent factor model, which is a more expressive collaborative model. I mapped each user and product to integer indices and created training triples of user X ID, item or user index, item index, and rating as and then the data set also contains, as we can see down here, 682,729 unique users right here. The number of unique items is 100,000 roughly and 800,000 training interactions. The model includes a global mean, biases for each user and item, and 32 latent factor vectors. I trained this with scholastic gradient descent of 20 epochs using a learning rate of 0.01 and a regularization also of 0.01. The best validation RMSE appeared at epoch 19. And so the test, the performance here for RMSE was about a 1.1382 and the MAE was about a 0.8553. This is a clear improvement over the user item mean and shows the benefit of learning latent preferences. The downside, though, is it's a little more complex, slower to train, and requires careful tuning. The fourth model, we went through metadata-only ridge regression. Features included price, verified purchase, main category, average rating, rating count, and the user product statistics computed from training. I built a column transfer that one hot codes the category and passes numeric features through and then run ridge regression on top. The performance here was about an RMSE of a 1.3602 or 3676 in the test and an MAE of 1.0213. This performs worse than the first model we looked at, the global mean. This shows that metadata alone is a weak predictor of star ratings in this data set. The advantage is that it's interpretability and speed, but the disadvantage is poor accuracy. Model 5, we go into text-only TF, IDF, and ridge regression. We switch to review text, which is the richest signal in this data set, as you'll see. I use a pipeline with a TF, IDF vectorizer that uses 20,000 features, 1 to 2 gram tokens, and a ridge regression model. This produces a high dimensional but sparse feature matrix, and the performance here was pretty staggering. The RMSE is down now to 0.8391 and the MAE of sub 0.6 now at 0.5995. And this was by far the best performing model. Compared to matrix factorization, this improved from 1.14 in the RMSE to now 0.84. And the MAE was at a 0.86, is now at 0.60. So this demonstrates that the text itself is extremely predictive of the rating. The downside is it's highly dimensionally and memory cost, but the performance was absolutely excellent, as we saw. And in model 6, we used a combined text plus metadata ridge regression. And here I attempt a hybrid model by concatenating the text, TF, IDF text features and structured metadata features. So the combination of the last two models here in this code set, I reused the fitted TIS IDF transformer and a metadata preprocessor, combining them with HStack and fitting another ridge model. Surprisingly, though, compared to expectations, this model performed worse than text alone. The test RMSE was about a 1.36 and the MA is now all back up to 1.02. So this dominates the model due to regularization scaling, causing the strong text signal to be underweighted that we found was very strong. This highlights an important modeling challenge, though. Naively combining modalities does not guarantee improved performance, especially with high dimensional text. So just because we're combining these, very strong individual models, the combine we saw does not necessarily translate to improved performance. And as a result, as we look at these different models and their test RMSEs and MAEs, the main conclusion here was that the Amazon baby product subset, the review text alone captured through TF-IDF and simple ridge regression is by far the strongest predictor of star ratings. Collaborative and metadata-based models are useful for comparison and relate directly to course content, but they do not match the accuracy of the text-only model.
Okay, in addition to the rating prediction task that we did, we also implemented a binary classification task, which is to predict whether a review is a positive review or a negative review. And this is based only on the review text as the input. And so we define a positive review as one with a rating with 4 stars or greater, and a negative review as one with less than 4 stars. And we're looking at the accuracy, precision, recall, and F1 scores here. So first, our data has to be changed because the rating column is only 1 through 5, and we want the ratings to be either positive or negative. So we go through the ratings column and turn it into a 1 if it's greater than 4, or 4 or greater, and we turn it to a 0 if it's less than 4. And so we see here the new distribution. Most of the reviews are positive with about 78%. And then our baseline is kind of similar to what we did in assignment 1. We go through all the positive reviews and all the negative reviews and find the most common words in each class. So here we're extracting the top 25 common words in positive reviews and the top 25 negative common words in negative reviews. And then we use those sets of words to identify whether a new review is positive or negative, simply based on how many positive words there are and how many negative words there are in that text. You can see here that for the positive and negative words, there's a lot of overlap. So things like product, baby, like, and great are all like overlapped within the sets. So there's not really a good distinction between the two classes with just these words. And you can see that with the accuracy, right? So for the validation and test sets, we only get about 76% accuracy, which is pretty bad considering that if we were to just guess all positives, we'd get 78%. So to improve on this, we use TF-IDF vectorization paired with a logistic regression classifier. So for our implementation here, we build TF-IDF vectorizers or vectors, and each has 10,000 feature dimensions, and we're looking at n-grams of 1 and 2. We're also removing all the stop words, and then we're using a logistic regression model to kind of train on the vectors that we build. And so after running this, we get a much better performance. We see that the validation and test accuracies are about 90% now, which is a lot better than the baseline and a lot better than just guessing all positives. And this kind of ties into the related work. A lot of the recent work that's been done on this Amazon review dataset has been in the field of natural language processing and recommendation. And the most popular methods or most popular approaches include sentiment classification, rating prediction, text generation, summarization, and building recommender systems through text. So a lot of the methods for these, or a lot of the models for these approaches have been dominated by transformer architectures as well. I've seen a lot of work mentioning BERT models and llama models, and they often achieve really high accuracies when it comes to sentiment analysis. One model in particular was able to achieve around 98% accuracy on a binary sentiment classification, which is the same task that we were doing above. And oh, also for the recommendation systems, uh, the way they use review text to do recommendation is that they create embeddings with the text and then use those embeddings to do collaborative filtering, um, which is kind of different from the latent factor models that we use in class. Um, but it's really interesting to see how they kind of change the approach, but we're able to get better results. Anyways, the comparison with our results was that uh, our model did not perform as well as these transformer models, which is kind of a given because the transformer models have often millions or almost billions of parameters. Uh, they're able to get a lot higher accuracy because they're able to learn the review text a lot better and thus classify them a lot better. But just seeing around 90% accuracy with our TF-IDF logistic regression classifier is still pretty good, especially since it only took about a minute to train and has way less parameters. Um, but yeah, overall, the findings kind of reflect that traditional linear models still remain effective and interpretable, but most of the recent work has been dominated by complex transformer models that really outperform any of this like traditional methodology. But yeah, that's our presentation. Thank you for listening.